Hello everyone, my name is Brent Griffin, and today I'm going to be talking about our work on the label imitation game, which we use to train a Turing test network that can perform zero-shot pseudo-label pruning. The motivation for this work is to improve vision language models, which are useful for pseudo-labeling unlabeled data at scale, but suffer hallucinations. If training downstream models, these errors add training noise that degrade performance. Typical noise reduction techniques use fixed thresholds, but we find that this often rejects authentic labels that have low confidence, while in other cases accepting labels that are confidently wrong. To solve this problem, we introduced the Turing Test Network, which is a lightweight post-hoc interrogator that's able to differentiate between accurate labels and hallucinations. Importantly, the Turing Test Network requires no human supervision or changes to the VLMs or training pipeline to prune pseudo-labels. Next, let's talk about the motivation and details for the label imitation game, which we use to train our Turing test network. After training, we perform pseudo-label pruning, which results in zero-shot task transfer, increased label accuracy, and a phenomena for downstream trained models we call category revival. The original Turing test evaluates a machine's ability to exhibit intelligent behavior that's indistinguishable from that of a human. Similarly, the label imitation game determines a vision language model's ability to produce pseudo-labels that are indistinguishable from those of a human annotator. The rationale and motivation for this is if pseudo-labels are indistinguishable from high-quality human annotation, then its quality is similarly likely high and should be used for downstream processes. The label imitation game involves a set of ideal labels, candidate labels, and a judge. Importantly, the judge is provided all of the data associated with the ideal and candidate labels without any additional information. Therefore, it has to look at the underlying data to determine what is common or what is semantically consistent across this group of inputs, and from that, determine which of these inputs are actually an outlier. Notably, the label imitation games are quite general, and we provide multiple definitions for different variants of the game in the paper. If you're interested in those details, please follow the link to the paper in the description below. We use the label imitation games to train our Turing test network that learns to evaluate pseudo-label accuracy within a dataset-wide context. In this way, the Turing test network takes on the role of automated judge at inference to perform pseudo-label pruning. Importantly, the architecture is lightweight, and the TTN is able to evaluate in and out of group membership purely through latent embeddings, without any label inputs. Specifically, the TTN architecture takes a set of image patches as input, which are associated with the candidate labels being considered. These image patches are then processed through a frozen clip encoder, and the subsequent clip embeddings are then processed through a custom-learned TTN tokenizer that connects the clip embeddings to the transformer. The transformer's reasoning block is what evaluates the input tokens via self-intention and determines what is common amongst my inputs and which one of these don't belong, which it communicates via the accept-reject logits, which are the final output of the Turing test network architecture. For Turing test network training, we use a weighted binary cross-entropy loss on the accept-reject logits over countless label imitation games. This is how the network learns to infer input category and resolve ambiguities without ever explicitly being provided a class label. To make the model a generalist, we train on 8 classification datasets simultaneously and find that a single network is able to achieve a greater than 94% validation accuracy on 7 of the 8 datasets. After classification-based training, the Turing test network successfully prunes detection pseudo-labels, achieving zero-shot task transfer without any human supervision. While semantic errors are expected to be rejected, an emergent behavior is the ability to reject poorly localized pseudo-labels, which had never been seen during training. Notably, while TTN pruning causes a minor reduction in recall, the precision gains are much more substantial, leading to a higher overall F1 score. In fact, while most classes benefit from an increase in F1 score, we find that the worst performing classes across VLM models and datasets improve by 28%, 44% with detection-specific fine-tuning. Additionally, TTN pruning exhibits a behavior we call category revival, where downstream detectors trained on pseudo-labels that are pruned by TTN are able to recover from zero recall on dozens of vulnerable classes. Finally, our fine-tuned TTND model doubles the precision, F1 score, and MAP for the vulnerable classes of BDD. However, our experiments show that a substantial amount of performance remains on the table for future work, which will need to be won from increasingly subtle VLM hallucinations. Thank you for watching our video. If you'd like to learn more details from our paper or try the code out for yourself, please see the links in the description below, and we look forward to seeing you at ECCV.